Newtonian mechanics. So in Newtonian mechanics, what we do is, in any mechanics, by the way, the goal of mechanics is to predict the future of a time-dependent system. So generally, these time-dependent systems could be something very simple, like a particle which has a certain mass and it is moving in space. For example, let's say you have a three-dimensional space and you have a particle that is moving in space. So at any point t, the particle is at some position x. This is a vector, x vector. And in some future time, which is t plus dt, we want to know where the particle would be. So what would be its position, the position at time t plus dt. So in mechanics, the goal is to, once you know the position of a particle at a particular time, the goal is to predict the future position of the particle. This example is given by a particle, but you don't need to have just a particle. You could have any time-dependent system. For example, you could have chemical reactions. Chemical reactions. So chemical reactions could have many chemicals, X1, X2, they give some product, X3. And we can find out, we can develop a set of chemical reactions that say, if you take some concentration of the chemical X1 and some other concentration of chemical X2, you put them together in a beaker, how long will it take for X1 and X2 to turn into X3? And in equilibrium, for example, what would be concentration of X1, X2, X3? So these are the type of questions you can ask. This is again a time-dependent question. The concentrations of X1, X2, and X3. The concentrations of X1, X2, X3. The concentration of X1, and this is a time-dependent quantity, similarly for X2 and X3. So if you have multiple chemicals in a chemical reaction, they are also a dynamical system. And for any dynamical system, you want to predict what would be in the future. There could be other such examples. One very popular thing is, and something that can give you a lot of money is, you have for example, stock prices. The stock prices change with respect to time. They are a dynamical system, and you would want to know how you can predict the price of a stock. So these are dynamical processes. We want to understand these dynamical processes, and one of the things that we will do in mechanics is to develop different machinery through which we can predict these dynamical processes. Okay. So in order to do that, we need to first define a few quantities. So in this picture, I showed you the position of a particle. It was determined by this vector x. Okay. So now, so in order to determine a system, we need to have the initial point of the system. So the system could be at, if it is just a particle in 3 dimension, it would be represented by x of t. That's the position of the particle at this time. We don't have to call it initial position. It could even call it, current. So at time t, what is the position of the particle? This is represented by this vector x of t. If you have a multiple particles in your system, so let's say you have not one but 3 particles, so their position would be x1, x2, x3, and in that case this whole the whole system of three particles makes a combined system, and if you want to describe the whole system, you will have to give the position of x1 as a function of time, x2 as a function of time, and x3 as a function of time. This once you specify both all three of them, x1, x2, and x3, only then you have completely specified the system. So what we want to do um, is describe the whole system through this set of x1, x2, and x3. Okay, so this is how you decide the position or the current position of the system. Then what we want to do is we want to figure out what happens in the future. So if the particle was at position x at time t, what would be its position at x t plus some other time delta t. So this is the future time at which we want to know its position. Now, let's say we have a particle so let's say we have a particle here which moves to a different position x of t plus delta t. What we can do is we can define so the change in position, we can define change in position. The change in position of the particle, of course, is, so the initial position was the vector x, the final position is this vector xt plus delta t, and the change in position is this vector that connects x of t to x of t plus delta t. So change in position delta x is equal to x of t plus delta t minus x of t. This is how we define the change in position of the particle. And if you have a particle, if you have a system with multiple particles, then you will define the change in position for each one of the particle and each one of the coordinates and so on. Now, once you have defined what is called the change in position, this change in position was brought in a time delta t, right? So now that we have a definition of change in position which happened over a time delta t, we can define velocity. Velocity, which is defined as v at time t, is equal to the change in position at time t by the change in time. So as the particle moves from position x of t to position x t plus delta t, this was done during period delta t, and the change in position was delta x. So the velocity is delta x over delta t. Okay, we can also write it as x t plus delta t minus x of t. These are vectors divided by delta t. Okay, so this is how we define velocity. In a similar way, we can also define acceleration. So what is acceleration? Acceleration is how much the velocity changes. So let's say the particle was at some position x, and its position was x, and its velocity was v of t. Okay. Then, as you go to the new position, it would have a different velocity, t of delta t. Okay, so at the new position, it will have a new velocity also. And in a similar way, the way we define velocity as change in position by change in time, we can define acceleration of the particle at change in velocity by change in time. Okay. So acceleration would be the change in velocity by change in time, and we can also the way we define for velocity, we can also write it v of t plus delta t minus v of t divided by delta t. It's just the same definition. We have just written it as delta v over delta t by as velocity at time t plus delta t minus velocity at time t divided by the time over which this change occurred. So this is called acceleration. Now once we have defined what is position, velocity and acceleration, we can now start describing the how the position and of the particle would change with respect to time. So till now we know that okay, the particle was at some position x of t, it has some velocity, you can similarly define acceleration and so on, and it moved from here to some other position. Now till now we have only defined the quantities which we will use to describe the motion, but we haven't actually talked about how does the motion change, right? So the particle is moving, and but why is it moving, and what causes it to move? That is something which comes through Newton, and Newton says. So according to Newton, when an object is moving, it's going through some kind of a change in its motion, its position, velocity, acceleration. He says that this can be described by a very simple law, which is let's say there's a force acting on the particle. So there's a particle, it is moving in space. The reason it is moving in space is because there is a force acting on the particle which causes it to move. So somebody, let's say, pushing the object or pulling the object and so on. So there's a force which is acting on the object which causes it to move, and this force, according to Newton, is equal to mass times the acceleration. So Newton says that if you take an object and if you apply some force on an object, that force causes the object to accelerate. And since acceleration causes change in velocity, and change in velocity causes and velocity causes change in the position, if you apply a force to an object, it will cause an acceleration, which will cause its velocity to change and its position to change and so on. And that's why the particle actually moves. And now once we have this machinery, we have defined what is x of t, v of t, and a of t, then we can use this formula F equals ma to describe how the position of the object would change in time, because as you remember, a contains the information of x indirectly, because a contains the information of change in velocity and v contains the information of change in position. So once you know how a changes based on what force is being applied, you can find out what or how the position of the object would change in time. Okay, so this is what Newton says. This law came around 1600 when Newton wrote his Principia. But even before that, there were some laws. Before that, this was a very non-intuitive law, by the way, because we don't. If you just go out, in nature, and if you just do this experiment, like for example, you can take some object on a table, and if you apply a force to the object moves and goes to a different place. And the moment you stop applying force to the object, if there is no force, then the object stops. So what people actually thought before Newton was that forces don't actually cause acceleration. They thought forces cause velocity, because when you apply a force on an object, the object starts moving. When you remove the force, um, the object stops, which means its velocity has gone to zero. So, um, so people thought that forces actually cause change in velocity rather than forces don't cause forces cause velocity rather than acceleration. So before Newton, there was a law which was the Aristotle's Aristotle's law. Okay, Aristotle's law essentially said that if you apply a force to an object, it causes a velocity. So force is proportional to velocity rather than force being proportional to acceleration. And this was the law that people thought was correct, and it made sense to them because in their day-to-day world, this is what their experience was. But let's see. So we have now two laws. One says force is mass times acceleration, and here force is proportional to velocity. So we can write it as, let's say, force equal to, let's say, alpha times velocity. Okay, and let's say, how could we have figured it out which one of them is the right law? So one way we can do is we can do an experiment. Let's say we did not know which one of them is correct, and we want to figure out which of these laws, F equal to ma or F equal to alpha v, is actually correct. So the way we do it is we do some experiments. We can think of a very simple experiment. So let's say we have a spring that is connected to a mass. Okay, so we have a spring connected to a mass. Now, for a spring, you know that the force applied by a spring, if you take a spring and you extend it, the force applied by a spring is minus k times x. Okay, so if initially the object was, the mass was at position 0, you stretch the spring. So let's say we stretch the spring by a little bit, so the mass is at a different place, and this position is, let's say, x. So the extension in the spring would be x, and the force would be minus of kx, because as you stretch the spring in this direction, the spring tries to pull the mass back. So the force is minus k of x. So let's say, what is the consequence? What happens if we apply Aristotle's law as F equal to minus kx? So if we rewrite this, so in place of x, we would write minus k of x, and we have alpha, which is the law, and velocity. And velocity we defined earlier was, velocity, as you see, was the change in position by change in time, which is delta x over delta t. And if we take the limit that delta t is going to 0, then this can be written as dx over dt. Okay, now this is a very simple first order differential equation, so we can write it as dx over x equals minus of k dt. Okay, we can easily solve it. Dx by x is log x, and here we have minus kt plus constant of integration. So x of t is some constant e to the power minus kt. Okay, so what this expression says is that if you start with some position x, so this is time, this is some position x, the initial position. If you stretch the string and if you let it go, then the position would change um, exponentially. It will decay exponentially, and at some large time in the future, this will go to zero. This is the consequence if we assume that the force law was um, this. Okay, if we assume the Aristotelian force law, so force is proportional to velocity, that gives us the prediction that the position in this for this spring mass system would change as an exponential decay. Now, what is the consequence of the other law? The other law, the Newton's law. If we apply the same formula, so we had Newton's law is F equals mass times acceleration. So for force, we have minus of kx for the spring system. We have the mass. And then for acceleration, acceleration is change in velocity by change in time. But velocity was itself was, let me write it here. So, but velocity, so we have del over del t of the velocity, but velocity itself is change in position by change in time. Okay, so this is a double derivative essentially. So you have m d2x over dt2 equals minus kx. Okay, so according to Newton's law, we have the second derivative of position with respect to time equals minus of kx, and you probably know the solution of this is a second order differential equation. So if you probably know you have probably seen this, the solution of such an equation, which would be something like um, x of t is some cosine, sine and cosine of theta. So cos of omega t, where omega is square root of k over m. Okay, so essentially the solution in this case, if you have the Newton's law, they predict that the x of t would change sinusoidally. So there would be it won't be an exponential decay as predicted by Aristotle's law, but it will be a sinusoidal motion about some equilibrium position. Okay, and what do we observe? So if we do this experiment, you can very easily do this experiment. You can go to the lab, take a spring, connect it to a mass. You can either put it on a table, a frictionless table. If you have a friction, then the situation will be a bit different. But if you put it on a frictionless table, you can pull it, or you can, if you don't find a frictionless table, then you can just take a spring, connect it to a mass, pull the mass, and let it go, and then you can see what happens. And of course, what you would observe is that this mass oscillates rather than going exponentially to the equilibrium position. So after doing this very simple experiment, we can conclude that, oh, actually it's F equals ma law, which is the correct law, the law of motion. And using this law, we can predict the position and velocity of objects in the future. Okay. Now, what are the consequences of this law? There are some very simple consequences. So F equals ma, that's our law. One of the simple consequences is that what if the force on the object is zero? If force equal to zero, force equal to zero implies mass times acceleration equals zero, which means m dx over m dv over dt, m dv over dt equals zero, or dv over dt equals zero. The change in velocity with respect to time equal to zero, because mass is non-zero. we are looking at objects which have non-zero mass, which essentially implies that the velocity is constant. Okay, so the velocity is going to be constant. If there is an object on which there is no force, then its velocity is going to be constant. So it doesn't mean that if there is no force, then the object would not be moving. The object could still be moving. It could be moving with a constant velocity, but it will just not be going any acceleration. And we can write this as a vector. Okay, so that's the one of the consequences of this this law, that if the force of an object is zero, then its velocity is equal to zero. We can also write it in a little bit different form. So mass times acceleration, which is m dv over dt, can also be written as d by dt of mv. The reason we can do this here is we are assuming that the mass of the object is a constant. So if you once we take it inside the derivative, because the mass is constant, we can if you do the product rule, d by dt of m would be equal to 0. So this is same as m dv by dt. Now this quantity m times v is also defined as the momentum of the object. Is given a symbol p. So p, which is momentum of the object, is mass times its velocity. And this quantity p, so according to now we can rewrite Newton's law, which was, so Newton's law earlier was F equal to mass times acceleration. We can write it as d by dt of momentum, because mass times acceleration is rate of change of momentum. So force is in fact the rate of change of the momentum of the object. And this is a more general form of Newton's laws. The reason, it's a more generic form because the F equals ma, this relationship was for objects which have their mass as fixed. But what if there is a system for which the mass itself is changing? For example, rocket system. In a rocket system, as the rocket moves, it burns fuel. The fuel is ejected, and then that ejection causes loss of mass of the object. So if you're interested in studying the motion of the rocket, then it's important to have uh, an equation that takes into account situations where the mass itself would be changing, and this would be the law which would be more appropriate. F force is the rate of change of momentum of the object. This would be a more appropriate, it's a more generic form. You can, of course, F equals d by dt of the momentum is also equal to F equals mass times acceleration when the mass is constant. So this is a more generic form, and what happens if now F is equal to 0? So if there's no force acting on the object, then of course d by dt p equals 0, which means that p, which is the momentum, is equal to constant. Okay, so if there is no force acting on an object, if F equals 0, then the momentum of the system is conserved. Okay, the momentum is going to be constant, it's not going to change. So if the force on an object is 0, then this momentum is conserved, and this is called the law of conservation of momentum. Law of conservation of momentum. Okay. Now this is a very, very important law of physics, law of conservation of momentum. Uh, it is it applies to many different phenomena. We will only be studying classical mechanics, but this law applies to quantum mechanics, um, relativistic mechanics, and so on. So it's a very actually strong law, a very important law, law of conservation of momentum, and we will talk about it some other time. Now, till now we have only looked at a single particle and a single particle with which is moving in space. If the particle is moving in space, but we don't need to have just a single particle. As I said earlier, you could have multiple particles, x1, x2, x3, and so on. And if there are multiple particles, then of course, if you apply a force, the force could be applied to multiple particles, and these particles could be interacting with each other also to some kind of force. Like if these particles have charges on it, they might be attracting or repelling each other. If they have mass, of course, they will attract each other due to gravitational force. And there could be some external force acting on these particles. So the force, so the same law, the same Newton's law, F equals ma, or F equals rate of change of the momentum, also applies to a system of particles like this. And the force, the Newton's law in that case would be written as force, which is the total force acting on the entire system, would be equal to the rate of change of momentum of the entire system. Okay? So you take the momentum of the entire system, you study the rate of change of momentum of the entire system, that would be equal to the total force acting on the object. Okay, this is how you write the rate of change of momentum. This is how you write the Newton's law for a system of particles. Okay.